Good afternoon, everyone. My name is Yusuf Abdikarim, and I'll be doing the paper presentation for the Deep Learning course Fall 2021. The paper's name is Representing Scenes as Neural Radiance Fields for View Synthesis, and it's short for NeRF. The outline for the day will be as follows. I'll go through the motivation problem definition first, then go through the background, introduction for the paper, the architecture, results, and go through the limitations. So I think we've all seen the hype that has been going on regarding virtual reality systems quite lately. And the big promises that were made on how these systems are expected to be very realistic. But for them to be actually realistic and immerse the users, a really important thing that needs to happen is to mimic the real-world scenes that we see around us and allow users to interact with them and see them from different perspectives. This is typically the problem that we have in hand here, which is called view synthesis. The target of this problem is, given some sparse input views of a particular scene, we would like to render completely novel views of this scene. So in other words, while only seeing some discrete captures of a scene, can we typically look at this scene from any viewing direction? And optimally, can we look at or render this scene from any 360-degree angle around it or not? The first approaches that try to tackle this problem were interpolation approaches. We're given some input views of a scene. We would like to construct novel views by technically interpolating nearby views together. And a particular type of these methods are called light field interpolation approaches, where technically a light field is a 4D representation of radiance in terms of 3D location and viewing direction. So technically, if we visualize this light field as the VU plane here, then one of the views of the scene is a 2D slice of this particular plane, and the different 2D slices here represent different views of the same scene. And if you'd like to render a new view, we technically interpolate these two or some of the 2D slices together. The drawbacks of such methods are they require the generation of the light fields, and this is time consuming and memory consuming. They cannot represent any complex geometries, and the most important thing, they assume that there are no occlusions in the scene whatsoever, which hinders their ability to represent real-world scenes effectively. Another line of approaches are mesh-based approaches. And these approaches technically assume that we have objects that have a template or a fixed template 3D mesh. And what they're doing is, given some input views or images of this particular object, we would like to reconstruct the 3D mesh and reconstruct the texture and the color of this whole 3D mesh of this object. And after doing that, when we have like the full constructed 3D mesh of this object, we can render it and view it from any viewing direction. But it's quite apparent that this method is very constrained to the fact that the objects need to have a fixed template mesh with fixed topology. And this is not realistic also to be applied to real-world scenes, because not everything has 3D meshes that are already right there and ready to be used. And the method also could fall into local minima and reach less than optimum solution. Another very promising line of approaches for view synthesis are volumetric or layered representation approaches. And what these approaches do is, given an input sample view of a scene, they promote such a view to a multi-plane image representation using deep convolutional neural networks. And each one of these planes correspond to different depth values across the scene. And each plane contains the RGB and transparency values for pixels that are present at that particular depth value across the scene. What this representation allowed these methods to represent occlusions quite explicitly. And consequently, these methods have shown the ability to represent very complex geometries in real-world scenes, and they have shown the ability to have less artifacts in the novel views than the previous methods. However, one of the main drawbacks of these methods is that they have a discretized 3D representation, because these planes are taken at rigid and fixed locations, which does not allow them to represent the depth dimension in any continuous location, which consequently led to a 2.5D space representation, and generally they contain some limitation in representing the full 3D space effectively. So after that came the paper that we're considering in this presentation, which is Neural Radiance Fields for View Synthesis. And this paper was actually able to overcome all of the challenges that we just mentioned in the previous approaches. It can successfully model complex geometries. It can model a continuous 3D space representation. It requires no ground truth or depth for depth or meshes or 3D meshes. And it has low storage costs for the representation or the 3D representation of the whole scene. So how or what does it do specifically? So generally, the model is trying to learn the full 3D representation of a scene using a continuous scene function. And this scene function is approximated by a deep multi-layer perceptron. So the steps of the approach is as follows. I'll go through them generally and then go through each and every one of them in details. So the first thing is, given some sparse input views of a scene, we march rays across each pixel of these views, and we sample some 3D points across these rays, pass the location and the viewing direction of these points through an MLP to generate the color and the density of these points. Using a method called volume rendering, we fuse these points together to get one pixel, the color of this pixel for a particular pixel for this ray, and then we use a rendering loss to optimize the network. The first step in this approach does the following. For each input image and for each pixel in one of the input views of a scene, we march a ray, and this ray starts from the camera position, passes through the pixel in the image, and then passes through the whole 3D scene in front of us. And across this ray, we sample a number of 3D points. And for each one of these 3D points, we pass the 3D location of this 3D point and the viewing direction with respect to the camera through a multi-layer perceptron. And the target of this multi-layer perceptron is to predict the color of this 3D point and the opacity of this point. And the opacity here is also called the volume density, which is technically the probability, or it's telling us how much does an object exist at this particular point. So if a point is in free space like this one, it would get a very low volume density, but if it's lying within the boundaries of an object, it would have a very high volume density. But there is a very important thing that the authors of the paper noticed, which is the fact that we are giving the MLP a 3D coordinate and a viewing direction, and we're asking it to predict the color and the density of a point. However, this representation is considered very low frequency and it's low dimensional, which would hinder the MLP from representing very high frequency information or details in the image. So to solve that problem, what they did is they borrowed a method from the natural language processing transformers, which is called positional encoding. And what this does is that for each one of these inputs, for these low dimensional inputs, we pass them through a function that transforms them into a higher dimensional and a higher frequency representation. And what this function typically is, it is basically a sinusoidal function that given a value such as the x coordinate here, we have the ability to transform it to continuous representation of a predefined length that we specify in the network, and this representation is considered much higher dimensional. It allows us to represent much finer details in the images and was proven to work much better in terms of view synthesis and getting better details of the images. I'd like to go through the architecture of the MLP. So it consists of 9 fully connected layers, and the first layer typically takes the encoded 3D location of a particular point, and then this passes through a series of fully connected layers. And one very important trick that the method did was very intuitive actually. It's the fact that they predict the volume density, and they allow the volume density to be predicted based on the location only, because it makes sense that for a certain 3D point, if we look at it from different direction, its density shouldn't change. However, the color is what changes based on the viewing direction. So what they did was the volume density is predicted based on the position of the point only. However, the RGB color is predicted using both the location and the density by adding by the location and the viewing direction by adding the volume direction here in this layer and then predicting the color at the end. And here I show the effects of doing both the encoding and having the view dependence added to the network. So as we can see, without the positional encoding, we lost a lot of higher frequency information and fine details in the image that was in this particular area, for example. And also the view dependence, without it, we weren't able to represent some effects that were there because of a particular viewing direction that we're looking at this scene from. And this is the complete model, and this is the output of the complete model by adding both positional encoding and view dependence. And as we can see, we can model both view dependent effects and very high frequency and fine details in the image. So what we did so far was the following. For an input image, and for each pixel in that input image, we march array. And this ray starts from the camera position, passing through the pixel itself, and then through the 3D space afterwards. And across this ray, we sample a number of 3D points, pass each one of these 3D points through an MLP to estimate the color and the volume density of that point. However, at the end, we want this ray to be represented as a single color that corresponds to the color of that pixel. To do that, we will need to do some kind of a weighted average between the colors of all the points that we've estimated here. For this purpose, the paper uses a differentiable concept, and it's called volume rendering. For the sake of explaining volume rendering, I'll assume that this ray is continuous and that we have the ability to estimate the color of any continuous point T across this ray, and that this ray also starts from Tn and ends at Tf. And based on that, the equation goes as follows. We will calculate the integral of across points T in the ray, and for each point T, we calculate the color of the point based on the location and the viewing direction. Multiply that by the volume density, that's calculated based on the location, and then multiply by the transmittance T, which is an important and very crucial weighting term in this equation. This term tells us the probability that so far across the ray, at a point T, we haven't yet so far hit an opaque or solid point. What this means is, because in a typical scene, the rays that march through the scene would pass through different points that could belong to different objects and could also have different colors. But what we aim to have is the color of the ray should be mainly represented by the first solid points that this ray hits across the scene. And any other solid points that we hit afterwards shouldn't be contributing that much to the final color. Mathematically, at a point T, the transmittance is calculated based on the inverse of the exponential for the integral over all the volume densities that this ray hits so far before T. So for example, at this point here, this will have very high transmittance, since so far across the ray we haven't yet been or hit any opaque object, and all of these points have very low volume densities. But afterwards, all the points will have very low transmittance, since so far we have already hit other points that are solid and that have very high volume densities. So the problem is, in computer vision applications, we cannot deal with continuous functions. We need a way to discretize the ray, and we said previously that we sample a number of 3D points across the ray to do that. However, we didn't mention how does the paper actually do that in an effective way. The paper actually does something called stratified sampling. What it does is that it divides the ray into n equally spaced bins, and from each one of these bins, we randomly sample one 3D point, which typically allows us to represent this integral in a form of a summation over the number of sampled points. And typically the equation is the same. However, we allow the volume density to have a range of 0 to 1. We also add another weighting term that is typically the distance between two neighboring points to give higher weight to points that have higher volume densities and at the same time are far away from the next point. I've included this diagram here, which represents the same scene that we have seen previously in the previous image, where this is the representation of the camera and the ray and the representation of the Apple object that we have in the scene. So what stratified sampling does is that for each ray during training, we sample points in different locations and different random locations in this ray. So while training and passing through different rays, the model samples points at different random locations. So by the end of the training, the model has already seen representations and sample points across most of the locations in this ray, which allows the model to have a continuous representation of the depth dimension and not a discrete one. The problem is, and the limitation that the authors of the paper mentioned was, the stratified sampling approach takes samples at locations that might not be very effective for the final prediction of the color of the pixel or the ray. So these points, for example, are taken in free space, and few points are taken around around the object boundaries, which would cause the sampling to not be very effective. So to solve that, what they did was they passed these points that were produced from the stratified sampling approach through a coarse network, which is the same network, the same MLP that we've discussed previously. And this coarse network is responsible for predicting the RGB and density for each one of these stratified sample points. And based on these volume densities, we construct an piecewise probability distribution function. What this function tells us is the locations across the ray that have higher probability to have higher volume densities. Based on this probability distribution, we take samples again, but this time at points that have higher probability to have higher volume densities. And this allows us optimally to take much more fine sample points at locations that would most probably lie within the boundaries of objects. These fine sample points are then passed through another network, which is called the fine network, to produce the volume densities and the colors for these points too, and at the end produce a final color for the pixel by the fine network and the coarse network. Using the final color that was predicted from the coarse network and the final color of the ray that was predicted from the fine network, we supervise these two networks using this loss function. So the loss function is technically what it's doing is that it's minimizing the difference between the predicted color of a pixel and the ground truth color for a pixel. And we've mentioned previously that each ray R here represents a ray, and technically we have a ray for each pixel. So the loss, what it's optimally doing is it's doing a supervision on the coarse network by taking the square of the norm of the difference between the predicted color of a pixel and the ground truth color, and it's doing the same for the fine network, which is able to train our whole architecture. And we do that for all the rays that we have, technically for all the pixels that we have, and for all the input views that we get for the scene. And this is how we optimize this full network. So to make sure that we understand the steps that I've mentioned in the architecture properly, I've included a summarization video that recaps the whole process. So what typically happens is that for a reference view of a scene, we pass a ray for one pixel. And for this ray, we sample a number of 3D points. And for each one of these 3D points, we take the 3D location, viewing direction, pass it through the MLP architecture, and then predict the final RGB and density for this particular 3D point. We do that again for all of the 3D points across the array and generate a number of colors and volume densities, mix them together using volume rendering, get the final color of a pixel, and then we do that again for all the views and all the pixels to get the final 3D representation of the whole scene. To evaluate the performance of the paper compared to the state of the art, the metrics used were the Learned Perceptual Image Patch Similarity, which is called the LPIPS, and it uses the weight activations from deep neural networks in order to measure the similarity between images. They've also used peak signal to noise ratio and structure similarity index for similarity measurements. For the datasets, they've used 3 datasets. 2 of them are synthetic. One of them is a real-world dataset, which is called real forward-facing. And the realistic synthetic dataset was actually created by NeRF themselves in order to model objects that have lighting effects and non-Lambertian effects in general. For the quantitative analysis, we can see that NeRF has compared themselves with the state-of-the-art volumetric approach, LLFF, the state-of-the-art mesh-based approach, neural volumes, and state-of-the-art SRN approach, which is an implicit 3D representation approach. And as we can see, the NeRF outperforms these 3 methods on all of the 3 datasets. And it's good to note that LLFF was originally made to perform really well on the real forward-facing dataset. However, NeRF, while using a completely different representation, was actually able to outperform LLFF on the PSNR and the SSIM metrics. For the qualitative analysis, it can also be clearly seen that NeRF outperforms the state-of-the-art in terms of extracting very fine details from the images, and it also outperforms them in getting and in removing a lot of artifacts that were captured in the previous methods. It is also the case that NeRF is doing really well in capturing non-Lambertian effects and lighting effects compared to other state-of-the-art, and this can be seen in this particular object here and in this particular object here very clearly. NeRF has several limitations. So the first limitation is that it requires a lot of input views. On average, the previous experiments need around 400 to 500 input views to model the scenes in an accurate way. Moreover, the network is also needs to be trained once per scene. This means that if we would like to render a novel view of a new scene, we will have to optimize and train the network from scratch on that new scene. It also incurs very large rendering times during inference. This is because if we have a trained model and we want to render a new view, we will have to query the MLP a number of times that corresponds to the number of points for each ray that corresponds to each pixel in the output image, which takes a lot of time and computations. And lastly, the network also requires correct poses and correct viewing directions to be estimated for each of the input views that are presented as input to the network. Here are the references for the presentation, and also please feel free to check the paper itself for more details or the project page of the paper. Thank you so much for listening.